Welcome everybody as you're trickling in. Great to see you. We're here to discuss how to architect hybrid cloud, multi-cloud, and multi-orchestrator networking. So we're talking about advanced networking architectures, and we have a great speaker for you on that subject here. But before we get there, just a couple quick notes. So feel free to ask questions throughout the presentation. We're going to do our best to get to them. We may have to push them till the end. And if we don't get to them, we'll follow up with you afterwards. You will be answered. So we'll make sure that that happens. Also, before anyone asks, the session is being recorded, and we're going to send that out to you with some questions, probably some other resources as well that would be relevant. And you'll get the recording likely early to mid next week once we have a chance to process that. All right, so let's dive into the agenda a little bit. So today we're going to cover 3 of the most common advanced networking architectures. For each of them, we'll explore what they are, why you might want to use them, what you should be considering if you do, and the benefits and challenges associated with each, as well as good and better configurations for each of them. So one that is probably more obvious, and then one that you can build on, make with enhancements. So with all that, it's my pleasure to introduce you to our presenter, Matt Elgin, a solutions architect at Traefik Labs here. He's out of Richmond, Virginia in the US. He's been with us for about 2 years and has worked in technology and infrastructure for the better part of a decade. So all that to say, you're in good hands. All right, I'm gonna get out of the way. Matt, take it away.
Awesome. Sounds good. Well, thanks, Dylan, for kicking it off and for the introduction. So we can go ahead and dive right into the topic. So like Dylan mentioned, we're going to discuss some of these kind of subcategories of more complex network architecture patterns that we've seen working with our customers. So I want to start, before we start diving into the individual variations of this architecture, by talking about kind of the general progression and patterns that we see. So from a networking perspective, a lot of times we see projects starting off relatively simple. So that can mean we have our actual applications running in a single infrastructure type, a single production environment. Maybe it's all in a public cloud provider, it's all Kubernetes, for example, or for older projects, maybe it's all in a data center, all on virtual machines. And networking tends to be relatively simple there. So we've got requests coming in from the internet, we've got DNS records pointing at some sort of ingress controller, reverse proxy, et cetera, that's going to handle that routing for us back to the end applications. However, as we start scaling out that project, adding additional projects, obviously complexity can grow, whether that's moving from on-premise data centers out to cloud presences, or maybe we've got a cloud project that needs to reach back to legacy applications once we've established that. So that complexity can quickly compound there. And then obviously that can grow even more from there. We can start looking at multiple different types of container orchestrators, multiple cloud presences, bridging across public cloud and non-cloud presences. So that means there's more maintenance, more complexity to plan for more room for error overall as we're handling the configuration and security for all this stuff. So Dylan outlined the 3 main subcategories that we're going to walk through. So we're going to talk through hybrid cloud, multi-cloud, and multi-orchestrator. The reality to keep in mind as we're talking through all of these is that a lot of organizations or enterprises of a certain scale have a combination of at least 2 of these, if not all 3 going on at the same time. So each one of these sub architectures, we'll call them, will have their own unique network challenges and things to think about as we're approaching them. But obviously overlapping them and having multiple happening at the same time is going to compound that complexity as well. So let's dive into our first example architecture and talk about hybrid cloud for a few minutes. So for each one of these, we're going to give a quick definition, an example of what that might look like, talk about why we might arrive at this sort of configuration, and then we'll talk through a couple of architectures, some variations that we've seen, and talk through some of the considerations there. One caveat I'll give here is that these are by no means meant to be totally authoritative or exhaustive. These are just examples that we've seen and are kind of starting points as you start thinking about the architectural decisions that you're making as you're arriving at these different types of challenges. So with that being said, we'll start with hybrid cloud, where we've got, basically we have workloads that are running both in data centers that are controlled by the organization, as well as public and private cloud workloads. So a very common example of that could be, we've got legacy services that are running in a company data center somewhere, running on virtual machines or bare metal servers. And then we've started containerizing, introducing microservices, and we've put those up in some sort of container orchestrator up in AWS or one of the other major cloud providers. So there are a couple of different reasons that we might arrive at this sort of architecture. One of those is the hybrid cloud setup could be merely a temporary state during a cloud migration project. So maybe we've embarked on this type of modernization effort. We are starting to implement microservices or migrate things up to the cloud. And in the middle of that migration project, we'll need to account for networking across both of those locations and the workload types. Another reason we could opt for this is a more permanent or intentional driver for this architecture. Maybe we are in a company that operates in an industry that is highly regulated or handles particularly sensitive information. Maybe it's financial services or healthcare, et cetera. And this could be a conscious choice that we want to maintain our most sensitive data in-house on a data center versus putting that out in the public cloud somewhere. So we want to do that while still taking advantage of the scalability and all the other benefits that running things in the public cloud has to offer. So with that in mind, let's walk through a couple of variations of architecture that we've seen. So this first one is what I would say is probably the most straightforward approach that we've seen. So here we've got that exact example we were just looking at on the previous slide, where we've got some legacy services running on virtual machines in our data center. We've got some sort of reverse proxy in front of that that is handling the routing within that data center to our individual services. Up in the cloud, we've got a Kubernetes cluster where we have applications running as pods in that cluster, and we have some sort of ingress controller that is handling a similar role to the reverse proxy on-prem, where we are handling incoming requests and routing to the correct pods on the back end. So in this case, we're really just handling the initial routing by DNS. So we've got DNS records pointing up in the cloud and to the data center. And the benefits here are that this is pretty straightforward. This is really the natural evolution of running things entirely on-prem to starting to incorporate some sort of cloud presence, allows for that easy first step in the migration. Some of the challenges or limitations to be aware of is that we are now handling the initial routing by environment. So that initial route by DNS is going to have some awareness of where things are running from an environment perspective. And we're also dealing with some level of redundant routing infrastructure. So we've got an ingress controller or reverse proxy that are handling similar functions across the different environments. So we can look at what we could see as an evolution of that architecture, where we have consolidated that ingress controller and reverse proxy into a single component. So in this case, we've got an ingress controller that is handling routing from the cloud, both to the internal pods within that Kubernetes cluster, but also to those legacy services running in the data center. So some benefits that are introduced by doing that unification. First of all, we have a more consolidated routing approach. So everything is handled by that centralized ingress controller component. We get to reduce the number of routing tools and infrastructure components that we're managing as part of our architecture. But it does introduce some additional complexity. So first of all, we need to pick an ingress tool that is compatible with those different workload types. So something that can handle Kubernetes service discovery, that can also handle routing to static IPs or host names for those virtual machines in the data center. Obviously, this also means we need to do more planning for cross-environment networking. Now that we are reaching out from the cloud directly into the data center, we need to make sure that we're planning for that as well. So some considerations and decision points that we'll want to keep in mind for this hybrid cloud scenario. First of all, we need to keep latency in mind. If the applications that we're running are something that are particularly sensitive to latency, we need to make sure we're thinking about that across the cloud and data center. We also need to be now thinking about the networking and firewall rules, making sure that our ports and protocols are opened up effectively so that we're able to communicate across those different environments. On the flip side of that, we want to make sure that everything that shouldn't be open for communication is locked down, and that security piece really becomes critical now that we're talking across these two different types of environments. And like I mentioned on the previous slide, it's critical to make sure that we're picking a tool that's going to be able to effectively handle those separate workload types across those different environments as well. So let's now pivot over to our second architecture type, which is multi-cloud. So we'll walk through that same exact exercise we just did for hybrid cloud. So multi-cloud is, just as the name suggests, rather than running a set of workloads in a single cloud provider, we are running across multiple cloud providers. So an example could be we have Kubernetes deployments running in GKE and GCP. We have some containers that are also running as ECS services in AWS, and maybe we have some virtual machine services that are running in Azure. Obviously, we can interchange all of these workload types across the different cloud providers as well, but you get the idea. So why would we try and opt for a multi-cloud setup? So one of the drivers could be to increase resiliency and fault tolerance. So obviously a major public cloud outage is something that hopefully we don't need to plan for super often, but part of that overall risk mitigation strategy could be spreading out the deployments and where your workloads are running from a vendor perspective. It could also be part of a overall cost optimization strategy. So maybe there are comparable services across the different cloud providers where one is cheaper than the other in one case, and we want to avoid the sort of vendor lock-in that comes with putting everything on a single public cloud. And the final reason could be taking advantage of unique services across the multiple cloud providers. So maybe there's a cloud vendor that has a particular service that is not closely replicated in any of the other ones. And we want to be able to pick and choose across those different types of services. That might be a reason to opt for multi-cloud as well. So again, let's talk through a couple of example architectures here. So in this diagram, we have a representation of the scenario described on the previous slide. So we've got some ECS services in a cluster in ECS, some Kubernetes pods in GKE cluster in Google, and we've got some virtual machines in Azure as well. So in front of each of those sets of workloads, we've got a reverse proxy or ingress controller running. Now here, the reverse proxy ingress term can be a little bit interchangeable. Here they're functioning very similarly in the sense that they're handling requests coming into the cluster through some set of routing rules, are proxying them back to the correct service on the back end. So here, just like we did in our first hybrid cloud example, we are separating things out by DNS primarily. So this can be DNS records that are pointing to the specific cloud provider subdomains maybe, or maybe we're organizing things by application DNS records in that routing strategy. But regardless, that's going to be a pretty simple first layer approach to get us to those individual clouds. The challenges there is that primarily it is a somewhat prescriptive approach for doing that initial routing to the individual cloud providers. So we can take that example and again, evolve it a little bit with an additional component. So what we've added here is another layer of a reverse proxy out front that can be thought of as our edge reverse proxy, or that layer one reverse proxy that we're going to use. So basically that's going to handle the initial routing to the individual in cluster, in cloud controllers or reverse proxies that we saw in the previous diagram. So some benefits of this approach, it allows for more sophisticated routing schemes. So if we, for example, wanted to expose a unified API host name that we want to route across these different clouds, we can do that and leverage path-based routing as an example, using that reverse proxy. We can, because of that, we can abstract away where the actual services are running from a cloud location perspective. There are some challenges or limitations to be aware of here. The first is that it is going to add an additional routing hop, and we need to think about the latency that might be added there. And the additional one is that it's going to require some degree of manual configuration to keep that list of locations up to date on this first layer, unless we have a tool that supports that dynamic syncing of those service lists. So some considerations here. So obviously, as we start to incorporate multiple cloud providers, we're going to make sure that we are up to speed on best practices for networking and security across the different ones there. We need to start thinking about an effective routing strategy across those different providers. So like we touched on, is it host-based primarily? Are we doing path-based, et cetera? Is our initial routing going to be aware of where things are running from a cloud provider perspective? Where we terminate TLS is another consideration to think about. Is that something that's going to happen on the first layer? Do we want it to run all the way to the individual cloud providers as well? And finally, when we're thinking about where we might put that layer one reverse proxy, we want to think about where we have a majority of services running, what kind of workloads are running in each of those different cloud vendors. So let's wrap up with our third variation of complex architecture, where we'll talk about multi-orchestrator. So again, here, this name is pretty self-explanatory. This is when we have applications running as containers within more than one container orchestrator. So this could either be different orchestrators all in the same cloud or environment, or we could start to see that overlap where we have a hybrid or multi-cloud scenario overlapped with this multi-orchestrator setup. So an example here could be our new greenfield applications are going to be running in a cloud-based Kubernetes cluster, and then we have some existing services in Docker Swarm somewhere. So why would we arrive at a multi-orchestrator setup? Again, just like the hybrid cloud setup, this could be a temporary state if we're migrating between orchestrators. Say we're consolidating on Kubernetes from Docker Swarm, that could result in the need for multi-orchestrator networking. Or maybe there are some applications that have specific requirements and dependencies on a particular orchestrator type, and that prevents that full standardization on a particular type of orchestrator. So here we're going to, again, look at an example architecture. Here, this is very similar to the last architecture we looked at in the multi-cloud routing setup, where we have a reverse proxy or ingress controller in each one of our orchestrator clusters. So here we've got Docker, Kubernetes, and Nomad. And then we have a layer one reverse proxy out front. So the benefits and challenges here are going to be very similar to what we saw on the multi-cloud setup. So this allows for flexibility. If we're doing a migration, this supports more readily changeable networking updates, but it does introduce that additional hop. And again, we have that manual configuration to think about if we don't have a tool that's automating that for us. So some considerations to think about here. First of all, we need to select tools that are going to be able to handle that service discovery across the different orchestrators, being able to hook into those different orchestrator APIs and route to the containers accordingly. We need to think about our routing strategy to actually get to the individual clusters themselves. And finally, we need to be cognizant of the networking limitations inherent in orchestration clusters as well. So thinking about where services within the cluster are able to resolve those other services across our entire networking architecture as well. So I want to wrap up that last variation by talking a little bit about how we have seen customers approach that with Traefik Enterprise specifically, namely talking about the multi-layered routing capability. So the way that we approach that with Traefik Enterprise is leveraging what we call the Traefik provider. So providers within Traefik are the pieces that are facilitating service discovery for that particular infrastructure type. So that can be service discovery within Kubernetes or Swarm or ECS, et cetera. So this Traefik provider is another one in that list that allows us to automatically handle that multi-layered routing, having that edge reverse proxy instance that we saw in a couple of those architecture examples. So the way that it works is by relying on the Traefik API that's exposing our routing information where our services are located from those layer 2 in cluster, in cloud instances, and then automatically syncing that up to layer 1. So that's going to allow us that routing flexibility without needing to manually update the layer 1 list of services and where things are running. So an example architecture of what that might look like, if we do a comparison from our previous architecture slide, we have dropped in Traefik Enterprise to each one of those ingress controller or reverse proxy instances. So we've got that running within each of our clusters, and then we have that out front as our layer 1 reverse proxy as well. So the benefits here, we have a ton of flexibility in how we're routing across the different environments. The migration process becomes much easier from a networking perspective as we're dynamically keeping up to date where things are running. And most crucially from the previous examples, we don't have to manually maintain where things are running on that layer 1 instance. So that's going to introduce a great deal of efficiency, reduce the risk in configuration changes breaking something across this entire network stack. So we'll wrap up with a few quick takeaways. So we've walked through a few different variations of more complex networking scenarios. Each one of those are coming with unique challenges that have to be considered when we're architecting those environments. In a lot of organizations past a certain scale, the reality is that at least 2 or 3 of those are going to be at play as well. Some of those approaches we looked at are the temporary product of a migration effort. Others are set up more intentionally for a longer term setup for those drivers that we discussed. And some of the common themes to think about when you're going about architecting these are the overall routing strategy, making sure that the security is set up across all of these, and planning for service discovery across all of these different variations. One last slide. If any of this sounds familiar to challenges that you are dealing with within your organization, this is something that we discuss and help our customers with every day. So whether it is hybrid cloud or multi-cloud or multi-orchestrator, Traefik and Traefik Enterprise can definitely fit into that sort of stack and alleviate a lot of those challenges that we've addressed.